Hello, welcome to the recitation week 4. Today I will be solving some problems related to inverse Laplace transform, and I also will be solving a problem on linear differential equation using Laplace transform and its inverse. The first three problems I will be demonstrating how can we find the corresponding inverse Laplace transform for three different cases. So this case they are depending on the types of the roots. Okay, for example, on the first problem we have distinct real roots. Second problem has repeated real roots, and the third problem has complex roots. Let's begin. The first problem solution. Okay, the first problem we have f of s is 1 over s squared plus 5s plus 6. We know that this has two distinct real roots, so we can just factorize it. S and then 6 is 2 times 3, so you have 2 and 3. The sign are plus, and you need to use the partial fraction expansion to solve it, since they are comprised of distinct roots, real roots. Then you can just use this approach. So for s plus 2 you have coefficient a, and for s plus 3 you have coefficient b. Basically we just need to find these two coefficients a and b, such that if you add both terms right here, then you get the original fraction. There are many approaches you can use, but the simplest one, if you have distinct real roots, are for a, for example, you can just multiply s plus 2, because a corresponds to the pole s plus 2. So s plus 2 multiplied by f of s, and you substitute s with the roots of s plus 2. The root is negative 2. Okay, so you multiplied s plus 2 to f of s. Since you multiply s plus 2, then s plus 2 will cancel. You only have 1 over s plus 3, and then you substitute s equal to negative 2. Okay, of course you have minus 2 plus 3 is 1. So a is 1. And b, the same approach, s plus 3 multiplied by f of s, and you substitute s equal the root of s plus 3. So the root is negative 3. So this product you get 1 over s plus 2, s equal to minus 3. So 1 over minus 3 plus 2 is of course minus 1. Okay, so you are left with a is 1, and then b is minus 1 s plus 3. From here you can just use the Laplace inverse table. If you have, okay, so if you look at the table, then you can directly compute f of t. Okay, so 1 over s plus 2 is e to the power minus 2t, and then you have minus 1 there, so minus e to the power minus 3t, and this is defined for t greater than or equal to 0. Okay, so that's the solution for the first problem. Pretty simple. All right, and then let's move on to problem number 2. For this problem, we have repeated real roots. 1 over s plus 1 multiplied by s plus 2. So s plus 2 here is squared, so you have 2s plus 2, right? You have repeated real roots, and the partial fraction expansion is a over s plus 1, and then b over s plus 2, and then you have another term c over s plus 2 squared. Again, we need to find ABC. For A, we can use the same step as in the first problem. So you multiply s plus 1 to f of s, substitute s with minus 1. You have 1 over s plus 2 squared, s equal to minus 1, you have a equal to 1. Okay, and then for C, you substitute, so multiply s plus 2 squared to f of s, and you replace s with the root is negative 2, and you have 1 over s plus 1, s is negative 2, so you have 1 over minus 2 plus 1 is minus 1. Okay, so far we have f of s. Let's write f of s again, s plus 2 squared. Now we have a, right? A is 1, so let's write 1 s plus 1 plus b. Still we do not know b right now. Well, let's just write s is, and then c is minus 1, so let's just write minus s plus 2 squared. Okay, so we can erase f of s for now. This is what we have, so you can easily find b. You just need to solve this, and then you can find b. But there is a quick approach to find b. So for both sides we can substitute s with any value, so you can substitute s here with any value other than the roots of s plus 1 and s plus 2. So you can substitute s with any value other than minus 1 or minus 2. So if you think of the simplest s that is not minus 1 or minus 2 is 0, but you can also use 1, 2, 3, or anything other than minus 1 or minus 2. Since 0 is the simplest one, okay, let's just use 0. Okay, because that's the easiest one. We have, okay, 0 plus 1 is 1, 0 plus 2 square is 4, 0 here is 1 over 1 plus b over 2 minus s0 is plus 1 over 4. Okay, so from here, of course, you can compute b. So b here is equal to minus 1. Okay, so f of s, you can write it as here 1 over s plus 1 minus 1 over s plus 2 minus 1 over s plus 2 squared. Okay, to find f of t, then you can use the table, the Laplace transform table. 1 over s plus 1 is e to the power minus t, and then minus e to the power minus 2t, and then 1 over s plus 2 squared is minus t times e to the power minus 2t. This is for t greater than or equal to 0. Okay, so this is the solution for problem number 2. I hope I am clear so far. Okay, next problem number 3, we have complex roots. So it means that you have real part and imaginary part. S multiplied by s squared plus 2s plus 2. Okay, so the partial fraction expansion, if you have like this term right here, this is complex, has complex roots, so you cannot separate them with real roots. Okay, for that case, one approach is just to keep this term, this polynomial s squared plus 2s plus 2 as one unit, so you do not separate them. The partial fraction expansion for f of s for this case is a over s plus this polynomial s squared plus 2s plus 2, and then for this numerator you have bs plus c. Okay, again you just need to find these parameters a, b, c. To find a, you can multiply s with f of s and then substitute s equal to 0, right? You have 1 over s squared plus 2s plus 2 s equal to 0. You are left with 1 over 2 or 0.5. Now we have 1 over s squared plus 2s plus 2 is 1/2 s plus bs plus c s squared plus 2s plus 2. Okay, we can simplify this equation to find b and c. The first thing that comes to mind, I want to eliminate this term 1/2 because it is really ugly. So how do you eliminate this? Easy, you just multiply both sides with 2. So let's do that. If you multiply both sides with 2, this becomes 1, this becomes 2, and then you have 2b plus 2c. Okay, and then you have s squared plus 2s plus 2. You have s squared plus 2s plus 2, and then you cross multiply this term with s, you have 2b s squared plus 2cs, and then you have 2b plus 1 s squared plus 2c plus 2s plus 2, and the denominator is s squared plus 2s plus 2. Okay, if you compare this fraction and that fraction, they have 2, so this term here on the s squared and s must be equal to 0, right? So you have 2b plus 1 must be 0, so b must be minus 1/2, and then 2c plus 2 also should be 0. That means that c is minus 1. Okay, so the final fraction f of s is 1/2 s, and then you have plus minus 1/2 s minus 1 over s squared plus 2s plus 2. Okay, so let's simplify this. You have zero 0.5 over s. And remember that this polynomial here, you can write it as s squared plus 2s plus 1, right? Plus 1, which is nothing but s squared, sorry, s plus 1 squared plus 1 squared. Okay, so you can write it as f minus 1 half s plus 1 squared plus 1 squared, and then you have s, and you have, this is minus 2 plus 2. Okay, so you have 0.5 over s minus 1 half s plus 1 s plus 1 squared plus 1 squared, and then 1 half 1 over s plus 1 squared plus 1 squared, right? Okay, so you can check the Laplace inverse table to find f of t. So the inverse of 1 over s is 1, so you have 1 half, and then minus 1 half. So this term is e to the power minus t cosine t. This one is 1 half e to the power minus t sine t for t greater than or equal to 0. Okay, so this is the solution for problem number 3. The last problem is initial value problem. So we need to solve the linear ordinary differential equation using Laplace transform. Let's write the problem once again. And you are given with initial conditions y0 is 1 over 4, y prime 0 is 0, and the input u of t is e to the power minus 3t. Okay, so in order for you to use Laplace transform, then you have to specify that t is greater than or equal to 0. Okay, so let's solve this. So you can apply Laplace transform to this differential equation. Laplace of y prime t for y prime t plus 5y t, and Laplace of 3ut. Okay, here you have sy s squared times y of s, okay, minus sy0 minus y prime 0, and then plus 4s y of s minus 4y0, and then plus 5 y of s, and the Laplace of, this is Laplace of 3, and ut is e to the power minus 3t, so you have 3 over s plus 3. Okay. Okay, we know that y prime 0 is 0, so this is 0. And y0 is 1 over 4, so you have s squared plus 4s plus 5 y of s, and then minus s over 4, and you have 4y0, so this is minus 1, 3 over s plus 3. Okay, you can simplify this as square plus 4s plus 5 e of s, and then you bring this to the other side. You have 3 over s plus 3 plus s over 4 plus 1 s squared plus 4s plus 5 y of s. So this term you can simplify this, and it becomes s squared plus 7s plus 24 over 4s plus 12. Okay. Okay, so this is not magic, so you have to work this out, and here I only show you the final form. Okay, and I left the process for you for exercise. From here, you can obtain y of s. So y of s is your solution in Laplace domain, right? So you want to find y of t. Here y of s is s squared plus 7s plus 24. You have 4s plus 12, s squared plus 4s plus 5. Okay, we have 4 on this s. That's not common, so let's simplify by removing the 4. You have s plus 3, but you need to multiply the numerator with 1 over 4. Okay, basically we just need to find y of t using inverse Laplace transform and partial fraction expansion, but the difficult part here is that we have again another complex roots. Okay, but we did that on problem number 3, so that shouldn't be a problem because we know how to solve the partial fraction expansion when the polynomial has complex roots. Okay, we just need to be patient. So what is the partial fraction expansion for this term? Easy, right? You have a for the first pole, s plus 3, and then bs plus c for s squared plus 4s plus 5. How to find a? Simple, multiply s plus 3 with f of s, sorry, fy, so y of s, substitute s minus 3, then we have what? So s plus 3 is gone, and then you have 1 over 4. S with minus 3, you have 9 minus 21 plus 24. This is gone, you have this. S is minus 3, you have 9 again, and then minus 12 plus 5. You can simplify this, and if my calculation is correct, it should be equal to 3 over 2. Okay, and we have 1 over 4 s squared plus 7s plus 24 s plus 3 s squared plus 4s plus 5. We have a is 3 over 2 s plus 3 bs plus c s squared plus 4s plus 5. Okay, how to find b and c? We can simply follow the step from problem 3. So you cross multiply it and you compare the numerator from the left hand side and the right hand side. You should be able to find b and c, and I found that b is minus 1.25, so minus 5 over 4, and c is minus zero point 0.5 or minus 1 half. Okay, so you should be able to check if my calculation is correct. Okay, and let's continue. Y of s is a 3 over 2 s plus 3 and then plus minus 5 over 4 s minus 1 half. You have s squared plus 4s plus 5. Okay, so since we have another complex root, so this is a polynomial with complex roots, then it will be likely that the solution will involve this term. So you have cosine or sine multiplied by e to the power something t. Okay, so we need to express this polynomial into this kind of form. Okay, so this term, this polynomial, it, it is equal to s squared plus 4 s plus 4 plus 1, right? S plus 2 squared plus 1 squared. Okay, so you have 3 over 2 s plus 3. So let's rewrite this. So you have minus 5 over 4. So the denominator s plus 2 squared plus 1 squared. And what about this term right here? If we move 5 over 4 right there, you have s plus, I got 8 over 5, because if you multiply 8 over 5 with 5 over 4, we get 1 half, right? Oh, sorry, that's not 8 over 5, that's 2 over 5. Okay, when you multiply 2 over 5 with 5 over 4, we have 2 over 4, which is 1 half. Okay, so this is correct, but the thing is we have s plus 2 here. So if we want to use this term, or this term, we should have similar term. So we need to rewrite this again. Since we have plus 2, we don't have plus 2 here, so let's add plus 2 and then minus 2. Okay, since plus 2 and minus 2, they don't change anything. So let's continue. You have 3 over 2 s plus 3 minus 5 over 4 s plus 2 squared plus 1 squared, you have s plus 2, and then on this term we have 5 over 4, again s plus 2 squared plus 1 squared, and the term here is we have minus 8 over 5, right? So that cancels. You have this is 1, this is 2, so 3 over 2 s plus 3 minus 5 over 4 s plus 2, s plus 2 squared plus 1 squared, minus minus plus, you have 2, 2, the coefficient here is 1, s plus 2 squared plus 1 squared. Okay, so from here you can directly use the Laplace inverse table, and you get 3 over 2 s plus t is e to the power minus 3t minus 5 over 4 e to the power minus 2t. This one is cosine t, and plus 2 e to the power minus 2t sine t for t greater than or equal to 0. Okay, so this is the solution for the initial value problem given this initial condition. Okay, so that's the end of my lecture. I hope I've made myself clear, and if you have any question, then you can always send me email or meet me on my office hour. All right, thank you, and I'll see you later. Bye.